All right. So welcome to this session where we teach you about the black art of profiling, that is analyzing programs to figure out what their performance is limited by. An alternate title to this presentation, which was coined by a lab expert, was, if I put the right window in focus, meet hot functions in your area. So, standard warning, this is a very big topic. We could do a 2-week school just on all the different ways you can analyze performance, but then Pierre would kill me, so I won't do that. Instead, I chose to make this manageable by focusing the presentation a bit. So I will only discuss Linux tooling, more specifically the perf profiler. I will mainly discuss analysis tools for code that is limited by the speed of computation, compute bound, or by the performance of memory accesses, memory bounds. I will mainly discuss tools that apply to programs that use an ahead-of-time compilation model, like C, C++, and Rust. We will get back to what this means. And I will mainly discuss tools that apply to x86 CPUs from Intel and AMD mostly. Last point, this talk, by its nature, will feature quite a few demonstrations. So not all information you see will be available on slides. So if you're the kind of person like me who doesn't like to watch videos, prepare to take notes. Here's the plan. We'll first discuss how we can get a general overview of how our system is being utilized. Then we'll see how to drill down a bit into how our CPU specifically is being utilized in terms of microarchitecture. Then we will see how we can find the part of a code that is most responsible for the current performance. This is called hot code in the profiling jargon. And finally, we see what would happen after that. So, questions? Okay. Anyway, so the first step when you get into performance analysis situation is to start by thinking about your entire system. Your program, as it's executing, will be interacting with many resources. Many of these will be hardware resources, like it will be using a CPU, some storage device, memory. But some other resources are more logical in nature. Like, for example, your system administrator may have put CPU quotas, disk quotas, and this will also potentially affect your program's performance. The point of this global study is that each of these resources has some limits. It cannot go infinitely fast. It would be great. We don't have. And at any point in time, one or more of these resource performance limits is going to be what defines your program performance. Your program cannot go any faster because it's hitting this resource limit. So the goal of this first stage is to identify which of these limits affect your code. And then we can proceed with 2 solutions. Either we can modify our program to put less use on the resource. That's reducing the pressure on the limit. Or if we're rich, we can throw more hardware at the problem, or more powerful hardware, and we can increase the limit. This is not an approach we discuss in this school, but it occasionally comes in handy when, for example, the limit is just a bad system setting that you should change. So there is some methodology to this, which was developed by a great performance engineer known as Brendan Gregg. And the general idea is you want to enumerate the resources that are available in your system, which may be internal component, external services that you're using, like databases, web servers, interconnects between different system components, and this is super important. I'll get back to this. And for each of these resources, you will want to study 3 different things. The first thing is utilization. This is a metric that tells you which percentage of the time the resource is active processing some requests. For example, when you look at your system monitor and you say, oh, I have 100% CPU, this is actually 100% CPU utilization. At any point in time, your CPU is executing some code. The second metric is saturation, which is how many other tasks are waiting for resources. If you have high utilization alone, it may not mean that your system is saturated yet because you may have some parallelism. Like you may have your disk active 100% of the time, but actually you have another disk which is inactive that you can use. When you have saturation, it means that basically no other parallel resource can take its place. You are really hitting the limit and suffering from it. And the third thing that's not often discussed in performance courses is errors. Errors are actually linked to performance. For example, if you are connecting to a network service that's flaky, that doesn't work very well, it will often drop the connection. And your application will, after a while, time out and try again. And obviously, this will reduce your performance. If you have a disk in your machine that's failing, usually in the beginning, it will still give the impression of working. Only from time to time, it will momentarily stop responding for a while. Then the operating system will notice this and restart it automatically. So errors are something worth checking as well in performance analysis because sometimes you may find some surprises. More explanations on this page. So that's the nice theory. A few practical advice when you apply this method. It's common that you will have multiple copies of some resource on your system. You may have multiple CPU cores, multiple disks. If so, you want to study the above metric for each copy of the resource individually. The reason why this is so is that your program may not yet know how to use multiple CPU cores or multiple disks. So if you see, oh, I have 12.5% CPU utilization, I'm good, I can still, I'm not limited by CPU usage, but actually your Python program running on a CPU with 16 threads, you're saturating one of these threads, and you cannot go any further because you have a CPU bottleneck. So study cores individually, study disks individually. Think about interconnects. Interconnects are the poor guys in performance analysis. People forget about them all the time, even though they can and often are a performance bottleneck. Common culprits are the interconnect between CPU and main memory. There is an entire talk about this topic tomorrow. And in GPU, you will also see that a very common source of performance problems on GPU is communications between the CPU and the GPU, because these are typically connected by a bus called PCI Express, which is only express in the name. And finally, if your system uses multiple physical servers that are connected via a network, you will also want to check the network, especially because you are not the only user of that network. So even if you think that you are not using the network that much, if other servers in the rack are hammering the network right now, you will still have performance problems linked to that for even the tiniest network requests. A point to bear in mind about interconnects is that typically interconnects work with some granularity called messages. And the performance of an interconnect heavily depends on how big your messages are. If you are doing lots of small messages, typically you will get much worse performance than if you are doing few big messages. This is why when you are studying the performance of interconnects, if you have the way to get this metric, you really want to visualize both how much data is going per second on the interconnect, but also how many requests are processed per second, how many messages are going through the interconnect. Finally, you are often not alone on some part of the computing system that you're using, and you must be careful about this. I briefly mentioned this in the realm of network programming. If you are connecting to a server and other people are using the same server at the same time, the server will take more time to reply to your request because it must share the resources between all users. And one particularly nefarious culprit in this area in the modern world is virtualization in general sense. So virtual machines, containers, that sort of things. Because when you run a performance analysis tool inside of a container or virtual machine, what you will see is the system resource usage that comes from the applications that you run inside of your container, but you know nothing about the other applications that may use the same physical hardware under the hood, the collocated virtual machine, that sort of stuff. So in these situations, you will need to get in touch with the system administrators of that lower level layer to get access to the relevant metric, because these are required to get a full picture of what's going on. So some tools you can use. In terms of graphical user interfaces, on Linux, the ones provided by KDE and GNOME these days are okay. They do many things well, some less well. They are a good starting point. However, you will often be using some kind of remote server over SSH, where running a graphical application is either not an option at all or not nice because you get a huge round-trip latency anytime you do something in the virtual interface. In that case, it's convenient to have interfaces that can work just in your terminal within your SSH session. And there are two basic kinds of system monitoring tools that you can use here. Those that try to imitate the appearance of graphical user interfaces, like BTOP, Zenith, and Mon, glances. And those that try to use a more tabular format where they print a sequence of information one after the other, like SAR, DStat, VMstat. On a server system, it's common to set up some kind of centralization system like Prometheus to collect performance data across all servers that compose a system and expose it via a single web interface, typically based on Grafana. If you are using a system that has this sort of thing, usually you will not have access to it right away, but again, do negotiate the access to this data with your sysadmins, because it can be very useful. Now, let's look a bit into what that actually looks like in practice. So, here, on my desktop, you can see that I have set up this little widget called Plasmoid in KDE that measures a bunch of things. One is a graph that shows the overall utilization sum across all CPUs, but decomposed by kind of utilization. On this system, there are three main kinds of CPU utilization that can happen, which is user utilization that comes from applications, libraries. Kernel CPU utilization, that's typically when you ask the operating system to do something like synchronize threads, write data to files, that sort of stuff. And IO weight utilization, which is a bit of a misleading metric on modern Linux systems, because when the Linux kernel is processing some work, it may decide to either waste some CPU time waiting for the IO to complete, or momentarily block the application and do something else. And only the former will be accounted as IO weight. So you need to be a bit careful with that. Another thing which I have done is a breakdown of what is the CPU utilization for each individual CPU hyperthread on my machine. As I mentioned earlier, you want to have the two information. A temporal graph with 16 lines is not very readable. That's why I display the two in a different way. Next, I have GPU utilization. This system has two different GPUs, one which is integrated into a CPU, one which is separate hardware next to it. So I have one graph for each. And the separate GPU actually gets some dedicated memory. So I'm measuring how much of this memory I am using at any point in time. Because if I'm using too much of this memory, then I will run into performance problems. I'm also studying the utilization of main system memory. And again, I break it down into several categories. On Linux, the main useful categories are used memory, which is memory that the system cannot liberate under any circumstance because it contains irreplaceable application data. Cache and buffers are, for our purpose, we will consider them to be the same. They are basically implementation details of the operating system that if you run out of RAM, the operating system can liberate this data. So when you look at your memory usage in the terminal and you see, oh no, I only have 1 GB of free RAM, be careful, because sometimes free RAM accounting is based on also this cache memory and so on, which is something that the operating system can liberate right away if you ask for it, so it's not a problem. And finally, I have 2 graphs. One which represents the read and write throughput for the storage device, an NVMe SSD, and one which does the same for the network connections. I do not, unfortunately, have requests per second because the current version of the Plasma System Monitor do not support that. That's a bug that should be fixed. So why do I have all this? Because it allows me to get as complete of an overview as I can with this particular tool of what my system is doing. And then I can quickly check after running an application, oh yeah, the storage graph is completely up the roof. I'm probably limited by storage. There is also, you're not forced to use that on your desktop. There is also a dedicated version that you can use like this, that you can configure however you like. It's quite flexible. However, all this is nice, but as I mentioned, it's not so nice when you want to use it on a server over SSH, because GUI over SSH sometimes doesn't work at all, and when it does work, it's often going to be pretty slow and unpleasant to use. So over a terminal, I prefer to use textual user interfaces, which look like this. So this is a system monitor called BTOPS. There are several ones like that. On the top, you have a graph of CPU utilization over time, aggregated and per CPU core. You have a breakdown of memory usage similar to the one I have shown earlier, some storage activity, network activity, and what are the topmost processed by some metrics like how much memory they are using, for example. You can sort it however you like. And for that, I'm going to put this in split screen again. We have tabular system monitors. So how does this work? Let me show the example of SAR, which is one of the most well-known ones of these tools. So first, we run it once. And it tells you, oh, wait, you have all this. This is all I have recorded into the system. Here are statistics over the entire system runtime. Basically, something you don't care about. Yeah, great. A tool with good interface defaults, always nice. But if you put a number after this, what it will do is provide you some statistics every n seconds. So if I run SAR1, every second, it will tell me, by default, a breakdown of CPU utilization across the different kinds of CPU utilization that can exist on a Linux system. This format is actually really nice when you need to do machine analysis of this data, like you want to process it with a Python script and so on. This would be very inconvenient to do it with a graphical user interface, obviously. So it's much better to have this kind of raw number data. And actually, with some ASCII art, it can be readable. You are not limited to CPU usage analysis. You can display many other things, network, block device usage, that sort of stuff. For our purposes, we are going to use one particular configuration, which is this one. So here I am enabling monitoring of storage devices, which are called block devices in Unix speak. CPU utilization breakdown by kind of CPU utilization, and by CPU core, which are virtual cores in Linux terms, so hyperthreads, basically. And I am enabling human readable outputs. That's the thing that allows you to see your disk throughput in, for example, gigabytes per second, instead of having a very large amount of kilobytes per second, which is nice for machines, but not so much for humans. Now that we have this, we can start studying some workloads. For that, I am going to split my terminal into and hope it. I will need to decrease the font size a bit, I'm afraid. But maybe not that much. Yeah, that works. So let me run the first workload. Once I manage to get my mouse back. Yes, it's there. And what this workload is going to do is a very simple mathematical computation. Basically, it has an array of single precision floating point number, and it multiplies them by some constant factor. And you can tune both the size of the array and how many times you're doing the computation. And here I'm setting it up in such a way that I can change the array size while keeping the total number of computations constant. And I'm not in the right directory, so this won't work. Okay, fine. This is easy to fix. And there we go. So what we will see here is that this computation is parallel. It can use all CPU cores, and it does not use the storage devices at all. So far, that's what we expect. So good. If now we configure this application so that it uses only one CPU core, what you will see is a bit more interesting. So it's always using one CPU core, but it's not always using the same one. What's happening here is that Linux is preventing my laptop from overheating. And the way it does that is it shifts the workload from one CPU core to another over time, so that the thermal energy that gets dissipated when your CPU is working is distributed across the entire chip and not just one region of the chip.
No, it is distributed only between two cores.
Well, that's because here we are refreshing the display every second. And actually what we see is a fraction of the time spent using one core before the switch and after the switch.
Yeah, but you have 16 and it's distributing only between two of them. And now it switched the two.
I'm not pretending that I fully understand the underlying logic of Linux, but yeah, tries to do something. Now we can put some I/O workload and see how that changes. So, mouse, where are you? You are here. So here what we're going to see is that I/O actually can involve some CPU work. The reason for that is that I'm writing random bytes from memory to storage. So first I need to generate those random bytes. That's the bit of user CPU time that you've seen in the beginning. And after that, there is a bit of system overhead, which is involved in the actual, sending requests to a storage device, waiting for them to come back, and so on. So I/O is not free from a CPU point of view. And this means that on particularly fast storage devices like NVMe SSD, you can actually end up being limited by the CPU when you're writing data with only one CPU thread. There are some devices these days that you can only saturate by having multiple CPU threads writing to different files at the same time. Be careful with that. So this was a sequential workload. Let me run it again to give some explanation of the numbers we see after it starts. So here we see we have about 1,000 transactions per second. It's writing some 100 megabytes of memory per second, which is not great. It should be able to do more. Probably there's something else hammering the disk at the moment. And the average request size is 126 kilobytes per second, probably 128 badly rounded. All right. You see also that it's kind of pulsing. And that's because this application has some kind of cycle where it goes through the entire file, then it waits for the OS to be done writing everything, and goes back to the beginning of the file and starts over. So this will change a bit the I/O pattern over time. Now, if we try to put some random access pattern in there, this will take a while because Linux is quite bad at I/O scheduling, unfortunately. So when you tell it stop writing, you know, it will take its sweet time to do so. But once we get there, we can do that and do random access now. And you'll see that I reduce a bit the amount of I/O that I do. And here, what you will see again once it's done initializing. Did I actually start it? I'm not sure. Yeah, that's better. So here you get thousands of transactions per second. So before we were about 1,000, now we can go to 2,000. You see there's a bit more pressure, and the request size is smaller. If you watch the utilization figure earlier, you may notice also that it has changed because the pressure you put on the storage devices is not the same when you do sequential versus random writes. Typically, you will get a smaller limit for random writes. So that's it for system monitoring for now. So let me get back to my slides. And there we go. So now we know how we get a general overview of the system, and we can get a rough idea of, okay, I'm more limited by my storage device, my CPU, and so on. Let's say, because that's the main theme of this course, that we see that we have high CPU utilization and our I/O device is not under particularly high pressure, network device neither, and so on. So we suspect some kind of bottleneck that's linked to CPU utilization. But that's not enough. When you see 100% of CPU utilization, actually you don't know what this means. This could map into many different kinds of CPU utilization. It could be front-end utilization. So that's when your code is too complicated and the CPU doesn't make sense of it. This could be arithmetic and logic unit optimization, an arithmetic and logical unit bottleneck, which is when you are doing so many floating point computations per second that you reach the limit of how many the CPU can do. This can be a bottleneck at the CPU and memory interconnect, because in Linux, this is accounted as CPU time, since the CPU is active. And it could be, again, something else. And the problem is, depending on which of these things you will be dealing with, the program optimization that you need to carry out are completely different. So you really want to know here what's going on. And the tool that hardware provides you to do this is something called performance monitoring units, or PMUs from short. What this will do is help you clarify which part of the CPU specifically gets saturated as your program starts putting more pressure on it. You will be able to tell, for example, oh, I'm more limited by the amount of branches I do in my program. I'm more limited by how well I'm using my CPU cache, and so on. Sometimes just knowing this and knowing your code will be enough to know which optimization you need to do. Sometimes you will need other tools that we will discuss next. There's a huge amount of performance monitoring units that you can use. And by huge, I mean that at the time I last checked on one of my Intel CPUs, the amount of lines of output in the description of these units was 20,000 lines on an Intel CPU of text. So you can spend a while learning about this, and I am not going to discuss all of them in this talk. Instead, I'm going to do a few targeted examples using the perf tool that is bundled in a Linux kernel, and unlike other tools, works with all CPUs. There's just one problem with perf, which is a more general problem with PMUs, but it's especially prevalent in perf because its support is built into the Linux kernel. The problem here is that for perf to work in PMU profiling mode, you need two things. You need to have a Linux kernel that's sufficiently recent. And by that, I mean two things. At least version 5 point something to get all the cool perf features that were introduced before that time. And a kernel that's newer than your CPU hardware. Because otherwise, you know, that kernel doesn't know how your CPU works. This support is CPU specific. So you will still not get PMU support. And that's a big problem at compute center, because many computing centers like to use Linux distributions that have kernel that make Neanderthal look very young. So, well, that's the first problem. The second problem is access permissions. We are often on shared infrastructures, virtual machines, containers, you remember the deal. And the problem with performance units is that they don't care about this. They allow you to spy on what your neighbors on the system is doing. And that can be a security concern. So for this reason, most of this infrastructure disables access to performance counters by default, often does not document very well how you enable back the support. When you do have support, it's sometimes broken, especially in virtual machines. So that can be another problem. For these two reasons, I have so far never managed to set up a large-scale practical on use of perf on any kind of shared resource. And that's why I'm doing a demo today and not making you actually use the tools. Sorry. Maybe another time it would be better. So the strategy I advise you to use in the real world is take your big application, extract a fragment that can run on a system you control, such as your laptop. Make sure this simplified version of the application is still reasonably representative of what you had before. And then profile that, because that's your system. You control it. You can install any tool you need and enable any tool you need. So the first thing we can study is the overall efficiency of our CPU pipelines. You may remember from our CPU architecture course, our CPU is capable of processing ideally multiple instructions every clock cycle and should always be able to process at least one instruction every clock cycle. We can measure this. And the metric for that is called instruction per cycle, IPC for short. Some people prefer cycle per instruction, which is the reverse of it. I don't care. Name it however you like, invert it however you like. That's a useful metric to have. What can you do with this metric? In general, if you see that your system is processing less than one instruction per cycle, you have a problem. It's designed to be doing work every clock cycle, not waiting for something. If you're waiting for something, it means your CPU is not doing its job, and you need to figure out why. On the other hand, above one and at one, it depends on which CPU instruction you're executing. There are some so-called complex instructions of which the CPU can only execute one copy every cycle. Branches are a common example. There is another thing, especially on Intel CPU, but I suspect other CPU may use the same strategy. When Intel CPUs realize that your program is broken and doesn't provide the CPU with enough work, what they do is they say, hey, you can give me work, so I don't need to work, so they don't clock. Until they get to the point where they can again execute one instruction per cycle, but at a very low clock rate. This means that on such CPUs, you should not look at instruction per cycle alone. You should also look at the clock rate of your CPU, which is obtained by dividing the number of cycles that have elapsed by the number of nanoseconds that have elapsed. That's easy. In multi-core programs, you will want this clock rate you observe to be larger than the so-called base clock specification of your CPU, whereas for sequential programs, you should be able to reach a higher frequency somewhere between the base frequency and another frequency in the specification called the turbo frequency. You will always be able to find these kind of specifications on the website of your hardware manufacturer, but for some manufacturer, it will be easier than others. And here I must give Intel credit because they have the best specification website that any hardware manufacturer has ever made. You just go there, you type your CPU model, and you get all the specification you need. It's brilliant. Let's say that we have some low insertion per cycle that we want to investigate. Perfstat has one command line option called -da, which stands for --detailed. And what this option does is to add a bit more data that you commonly need in performance analysis. Things like how well you are using your L1 CPU cache, for example, which is a very common culprit for bad CPU performance, or how well your branches in your program are predicted by the CPU. There is one problem when you start using these details flags, which is that perf is measuring more and more hardware metrics. And at the hardware level, these metrics map into individual units that must each be programmed. And you have a finite number of such units. So as you add more and more metric, at some point you will run out of these units, and your CPU will need to start multiplexing, which is to say that it will not constantly measuring the stuff you're interested in, but it will switch between measuring different things over and over again. And this will obviously reduce measurement precision. In the worst case, it can even introduce bias in the measurement if you have some periodical phenomenon in your program whose frequency is close to the frequency at which perf is switching between counters. So be careful with this multiplexing. Try to avoid it when you aim for maximal measurement precision. So how do we avoid it? By using the aforementioned perf list command, which gives you a full list of all the metrics you could possibly measure, along with some explanation of which each of these metrics do. That's a good read when you don't manage to fall asleep at night. You can find many useful ideas of things to measure in them, learn a thing or two about how your CPU works. So, you know, when you have a program that's slow and you don't know why, maybe a good idea to go through this metric list. And if something is inspiring, try measuring it, see where it takes you. Performance measurement is a bit of an experimental science. You formulate hypotheses, you test them. When you study memory-related metrics, like how efficient your utilization of CPU cache is, for example, it's important to take the numbers that you get out of perf, like you made that many accesses to the L1 cache, and divide them by the number of instructions you have to put the number into perspective. The reason for that is that otherwise it's easy to get frightened by, oh my God, like 50% of my level 3 cache access do not use the cache, I'm so doomed, when actually that's because your program is very well tuned to fit in the L1 CPU cache and you never use level 3 CPU cache. So you don't care that it's badly used when it's used because you never use it. Be careful with percentages in performance. Then branch prediction. As I mentioned, when you have conditional logic, if, switch, virtual tables in object-oriented programming, anytime you have that, your CPU must predict where the program is going to go. And it's quite clever, actually, but if it's, you know, you're doing if based on a random number, it will not manage, right? And that's expensive, so you don't want to. There is another reason you want to look at this number, which is that most CPUs can only do one branch every clock cycle or every 2 clock cycles. And that's not so great by superscalar execution standard. We have CPUs that can do 2 floating point multiplications per clock cycle. So you really, if you can, don't want to be doing a branch every clock cycle. You want to do lots of stuff per branch you take. And this will require some optimizations like loop unrolling. When you do have a problem with bad branch prediction, remember that this is costly. Every mispredicted branch is of the order of 10 to 20 wasted CPU cycles. So it's a high priority fix then than to try to find what these branches are in your code and rewrite your program so that you don't need to branch on this condition. This may be quite a big program rewrite, unfortunately, but if you're really limited by that, it's worth it. There is another cool metric that, unfortunately, to my knowledge, only Intel has it. And that's the number of floating point operation that you are doing every clock cycle. So that's actually a combination of multiple hardware metric. It uses a cool perf feature called the -big-M metric, where you say, I want number of flops per clock cycle, and it measures everything it needs to tell you this number. And you get also the intermediary result, which in this case means that you not only know how many additions and multiplications you do per clock cycle, you also know how many scalar operations you do, SSE vectorized operation, AVX vectorized operations, and so on. That's useful because we know the performance limits for this at the CPU level. On every current CPU from Intel and AMD, you cannot do more than 2 scalar double precision operations per clock cycle. With SSE vectorization is 4. With AVX vectorization is 8. With AVX 512, it depends because AVX 512 is a bit shit, unfortunately. And all the vectorized limits are twice as big if you're using single precision, which is a good reason to use single precision when you can. And you can again get twice the performance if instead of doing multiplications followed by addition, you do fuse, multiply, accumulate. This is something that your compiler may or may not manage to do automatically. Sometimes you will have to do it yourself in the code. Once you reach those limits of how many floats you can crunch per cycle, congratulations, this is hard. Well, you have no choice than to do less computations. So then you need to go into applied math, like how can I approximate my computation to get something that's reasonably accurate with less work, basically. So overall, my advice would be to start with PerStat in detailed mode. It usually provides a good balance between precision and showing useful metrics. If you need something that's not in the default output, check out perflist for more info. Do not miss the list of metrics at the end. These allow you to measure higher level things more easily, so it's a good thing to have. And again, follow the scientific method. You have a performance problem. Make a guess about what it could be. Test that guess using hardware measurement. If the guess is right, you've learned something. If it's wrong, you've also learned something. Try another hypothesis. Now, there are some limits, unfortunately, on the use of performance counters for performance monitoring. The level of detail that you can get into is hardware specific, which in the particular realm of x86 means that if you have the opportunity to do this sort of profiling on an Intel CPU and not an AMD CPU, please do so, because AMD's performance monitoring units are much worse than those of Intel in terms of level of detail. If you enable too many metrics at once, as I mentioned, you reduce memory, you reduce measurement precision, and in the worst case, you can introduce bias. By default, PerStat shows you metrics integrated over the entire job, which can be a problem if your program switches between different execution phases that each have a different bottleneck. If you have this, one trade-off solution is to use the interval option to ask PerStat to output smaller granularity results, like what happened in the last second, for example. And finally, perhaps the most important one, any kind of CPU performance analysis tool will produce meaningless results if run on a program that is not limited by the CPU resource. So I mentioned earlier, the start of any performance optimization is system-wide profiling. Do not skip this step. Otherwise, you may end up speeding CPU work by a factor of 30 before you realize that it doesn't change a thing. So, what does that look like now? To show this, I'm going to get back to my trusty terminal. I do not need my system monitor anymore because I have showed you what I needed to show with this particular tool. So I'm going to switch to using exclusively PerStat on the first computation I showed you, which performs multiplication of floating point numbers, something very simple because it's easier to analyze. So I'm going to get back the computation that I have shown earlier as well. And now I'm going to see how its characteristics, sorry, wrong folder, I closed my terminal, yes. I'm going to see how the output of PerStat is at small data size and how it changes when I increase the size of the data that I'm working with. As a reminder, I'm working at constant number of floating point operations here. What I'm doing is every time I increase the amount of numbers in my array, I decrease the number of repetitions in the outer loop. So I'm always doing the same number of floating point multiplications. This part doesn't change. So here what I get is that I'm spending overall 37 milliseconds of CPU time, which when divided by the time that actually elapsed means that I'm using about 16 CPUs in the Linux sense. That's good, that's what my machine has. I don't have that many context switches, so this sort of order of magnitude is something you learn from experience. 3,000 context switches over 3 seconds is tiny. Same for CPU migration, not a problem, not a problem. I have a certain number of instructions which I can use along with the number of elapsed CPU cycles to determine the number of instructions per cycle. Here you see it's 2 point something, so it looks like we're good. We have a good superscalar execution efficiency. There is this metric which I will not get into because it's a bit advanced. And then the cycles can also be divided by time to get the clock frequency, and 4 gigahertz for this CPU is perfectly normal. So again, you have this, so a bit of front-end stalls, but not a big concern. And there is a fairly high number of branches, but when you put it in perspective with the number of instructions, it's like one branch, 4 instructions, 1 branch. That's not the worst. A typical x86 CPU can handle that just fine. And our branch predictor is working perfectly, and the fraction of branches that we don't predict correctly is tiny. So far, so good. Everything is going just fine, except for one thing, which is these percentages on the right. So what this tells us is that we are using an AMD CPU. And as I mentioned earlier, AMD CPUs have really few performance monitoring units, and they are not very good at it. So already with this relatively small collection of CPU metric, we need to multiplex. So we need to alternate between measuring different things and then estimate the actual metric over the entire duration of the multiplication by multiplying by the inverse of the switching frequency. But 80% efficiency is not bad. 80% of the time we're measuring our application, that should not bias what we're measuring too much. So that's okay, we can proceed here. Now let's increase the size of the array.
Can you elaborate what exactly is a front-end cycles? What is front-end in this context?
So the CPU front-end is a part of the CPU that's in charge of getting instructions from memory, identifying them, and scheduling them for later execution across actual execution units. When you have a front-end stall, it means that your front-end would like to fetch new instructions, but for some reasons is not able to.
Like because you don't know which ones, or
which ones?
Which ones instructions you should fetch, or what could the
reason? Can be a matter of branch prediction. Can be a matter of the backend execution units are too busy, so you cannot push new instructions into the pipeline because there are other instructions waiting already. Can be many things.
But if there are other instructions waiting, it's not really.
Slowing it down. A pipeline can be stalled in 2 different ways. Either the output is full, so you cannot push new things because there is no room to push things into, or the input is not fast enough, so you cannot work because you don't get new bytes of instruction fast enough. Here, as I mentioned, because I have already such high pipeline execution efficiency, I would not look too much into this metric. You can ignore it for this particular program. That's not what I'm going to show next. So let's increase the size of the array that we process. Before we had about 2.5 seconds. Now we are 2.9 seconds. So we are 20% slower. What we see as well is that this metric has gone down now. We now have only 2 instructions per cycle, whereas before, if you remember, it was 2.5. So something is going bad. And as we mentioned earlier, this front end is less happy than before. So again, I don't want to get into the details of this because it's complicated. But yeah, clearly the CPU is not terribly happy with what we've done by increasing the size of the array. We don't know more at this point. But we can increase the size of the array further and see what happens. You see that actually, once you've passed that threshold, it doesn't change much. And I can tell you until we reach a data size of 16, it will not change either. So by the way, these numbers are, we are processing 2 to the power of 14 floats to the power of 16 floats and so on. When we get to 2 to the power of 16, we get another performance hit, which is more serious than the previous one. Now it takes 5 seconds almost to execute, whereas before it was 3. And we are down to only 1 instruction per clock cycle. So we have about divided our superscalar execution efficiency by 2. Increase further the problem size, as you can guess. The code will not get happier. At a size of 2 to the power of 20 numbers, again doing the same number of operations as before, we'll get another slowdown. And our instructions per cycle metric will drop to 0.77. So now we are getting into the danger zone where no matter what you're doing, less than 1 instruction per cycle is really bad. It's not a workload dependent. There's a problem here that we need to fix. And by the time we get to 2 to the power of 21 numbers, something terrible happens. And well, I can maybe leave this program running for a while. I mean, it was 7 seconds before I just doubled the input size. How bad could it be? Okay, I give it away. 70 seconds, a factor of 10. One cool feature of perf is that you don't need to wait 70 seconds to get some preliminary metric in this case. You can just Control-C your application and get some preliminary metric. You see that we are now down to 0.04 instructions per cycle. My goodness. That's like 1 instruction every 20 clock cycles or something. We are still running at the same frequency. Again, AMD does not put the same kind of tricks as Intel of downclocking the CPU. It will keep running the CPU at a high clock rate, but with very bad execution efficiency. And yes, something bad is going on here. I think you can guess what's going bad. But you know, let's say that we are completely clueless about this and try to figure it out using perf alone.
What memory bandwidth?
Cache hierarchy, then memory bandwidth. There, I spoiled it, sorry, for those who are still wondering. So let's add some details. And what we are going to see is that with AMD, the only detail you are going to get in this configuration is the number of times you try to access data from the L1 cache and the number of times you succeed. That's not a lot, but we can already do some work with that. If we try, you know, right now, it looks like we are basically doing 1 memory access per clock cycle, if we put these 2 numbers into parallel, which is fine, I guess. And if we increase that a bit, we are doing the same number of cache loads as before. However, you see that the load misses counter is growing. And it just keeps growing because you know you don't make caches work better by increasing the size of your working state, right? No, need to go a bit further. Sorry, I started at too low a data size, but at 60. You will get this picture. So for every access my CPU does on the level 1 cache, half of them are not going to hit the cache. Can you guess what's going to happen if I now increase my dataset size? What's going to happen to this number? Is it going to increase, decrease, stay the same? Why? That's actually the limit. But the reason why is interesting. Just, proof of what we are saying. So let me increase a bit. 2 to the power of 18 should do it. And we'll get something that's still 50%. The reason why that is the case is that my CPU uses AVX vectorization. In AVX, vector of floating point data is 32 bytes, which is half a cache line. So for every cache line that we load, we get 2 new inputs. So that's why when we do memory accesses, 1 in 2 is always going to succeed, no matter how bad our cache utilization is. Now, the problem is, as I mentioned, the defaults for perstat are not that great on AMD. We really want to have more metrics now, and we are going to get them. We just need to go through a perf list to find them. Yeah, sorry. Type something. Well, it's somewhere in there. All right. I have no patience to look for it, so let me give you away the answer. The set of metrics you will want to use to measure every supported cache metric on AMD is this one. So you want to measure loads from the level 1 cache that are attempted, those that miss, loads for the level 2 cache that are attempted, and those that miss. There are no metrics for the level 3 cache on AMD CPUs, unfortunately. That's a very big shortcoming that I wish they fixed someday. In any case, we can now use running configuration that uses those metrics. Accounting for the fact that terminals don't like line feeds, which is a pain. By the way, I should tell Markdown at some point that hyphens in commands are not something that can be elided. They are important. But anyway. And here we see again initial configuration, all good, level 1 cache works as expected. And we have no multiplexing anymore because we are measuring a set of counters that on this particular CPU is fits on the hardware measurement units. That's great. Now, as we start increasing the data size, we get a better picture of what's going on. So we get some load misses at the level 1 level, but they get handled by the level 2 level, so they do not reach below. At our next threshold of data size of 20, we get something that goes to the level 1 cache, fails, goes to the level 2 cache, starts failing to a very significant degree, 1 in 10. And as we go beyond that, it will start failing completely. And unfortunately, we will not be able to see this CPU going out of the level 3 cache because, again, there are no metric for the level 3 cache on AMD CPUs. But you will trust me on that one. One thing I want to mention is this weird thing. As you can see, the number of failed loads from level 2 is not what you would expect for a program that's completely outside of the any cache level. That's because of a cool CPU feature known as prefetching, where basically, when you're doing a simple memory access pattern, like reading data in a sequence, the CPU manages to predict what memory accesses you're going to do next. In this particular case, it combined with another CPU feature that just halts the CPU core momentarily when there's nothing to do. And then it gets back and you get back to what you want. If you don't have L3 cache metric, how do you know how big your L3 cache is? you get one tool you can use for it on Linux is LSCPU from Linux Utils, which tells you that overall we have 4 megabytes of level 2 cache, 8 megabytes of level 3 cache. So on AMD, you know, the difference between going out of the level 2 cache and going out of the level 3 cache is very tiny. So if you're not using your level 3 cache correctly, your level 2, if you're not sharing data across your threads, you will have a tiny amount of level 3 cache per thread on AMD CPUs, and you need to be careful with that. It's very easy to go out of your level 3 cache, and when you do, you get limited by the bandwidth of main memory, which, as I mentioned in my talk of CPU architecture, is not something you want to do when processing data in parallel. And by the way, that's why we get a slowdown of 10. It's because there is not enough main memory bandwidth for every core, so too bad. Okay, back to the theory. I said back to the theory. No, it won't. You will work whether you want or not. Not you. It's going to be the other one. Still have this open. Yeah, I have it. That's good. So, some of you may have noticed that before the school, I posted a little riddle on Discord. I say, look, this week, I have sped up a program by a factor of 20 just by putting a letter at the end of every hard-coded number in the program. And unfortunately, David spoiled some of the fun for me by immediately saying, oh yeah, that letter was F. So we didn't have to get that. Sorry. Blame David. How does something like this happen? It's actually a combination of two different stupid bits of infrastructure that this program happened to be using. One of them is the C++ programming language, which inherits stupid ideas from the C programming language for compatibility reasons. And two of these bad ideas are that in C, literals are typed. When you type a number, the compiler does not interpret it in the context of a surrounding expression. It says that all floating point numbers are double precision, and all integers must be converted to double precision if combined with other double precision numbers. Due to this feature of the C programming language, it's very easy to accidentally end up working in double precision when you don't want to. And unfortunately, this interacts with another stupid bit of infrastructure, which is an NVIDIA GPU. NVIDIA basically wants you to think that you can do useful scientific computation with 4 bits of floating point precision. Spoiler, this is a lie. And they take no care of optimizing the performance of the double precision unit to some abysmal degree.
It might be a lie for physics simulation.
Maybe if it's just fast simulation with neural nets, but for many kinds of computations, that's a big problem.
Yeah, but for AI, it's perfect.
Yeah, and AI makes more money than physics, unfortunately.
It's just implementation specific.
So yeah, their double precision number on many CPUs are 32 times slower than single precision numbers. So accidental double precision inside of an expression on an NVIDIA GPU is going to cost you a lot. So yeah, that's nice. I'm working with broken stuff. That's my life as a performance engineer. Now, how did I find this? And I use a variant of perf, which is specialized for NVIDIA GPUs, called Inside Compute. And when you measure this particular program with Inside Compute, the very first thing it tells you on the result page is you're doing lots of 64-bit floating point operations. And I'm like, well, that program is supposed to be single precision. And then I remember, oh yeah, but C is stupid and I need to fix the program. And then the program is 20 times faster. If I didn't know this, I could use finer grain profiling to find which lines of code are slower, and by then I would probably have figured it out. Which takes us to the next step of our presentation, our journey. How do we locate the pieces of code where we spend most of our time? How do we locate these infamous hot functions that I have mentioned at the introduction of my talk. And that will be the topic of this new chapter. So, you know, in an ideal world, as people who care about code optimization, I'm sure like me, you would like to optimize all the things. All code, perfectly optimal, down to the single, every single assembly instruction in your program is perfect. You have checked it. That's great. You don't have to do that on a realistic program. So what do you do then? What you can do is remember that in many things in life, there is an empirical rule called the 80-20 rule that applies. And in performance, one particular application of this rule of thumb is that you will often spend more than 80% of your time in less than 20% of your code. That's both good news and bad news. The good news is if you improve this small percentage of the code that is performance critical, you will get a huge performance improvement with little effort. The bad news is if you improve the wrong part of the code, you will get nothing. So it's really important to know where you're spending your time. And that's where profiling comes in. If, like me, also you are working with many different programming languages, you're probably getting tired at some point of having to use different tooling for each language. And you would probably like to be able to use the same tooling for many languages. Can we have such standardized tooling? The answer is not a yes or no, actually. It depends on how your program is executed on the machine. In C, C++, Fortran, Rust, Go, the standard way to execute a program is to first compile it into machine code. This is called ahead-of-time compilation. When you do that, the format of these machine binaries is universal. All languages share it, which means that it's easy to have standardized tooling. However, one thing I will point at is that many of these tooling require access to debug information to work. And worse, they do not need just debug information for your program. They also need it for every library that you use, for a reason that I may get into a bit later. If your languages now use just-in-time compilation, that's the case for Java, C#, Julia. In Python, the NumPy implementation does that. Root in C++ uses this model as well. It depends. Basically, in JIT compilation, there is a compiler available at the time where your application is running, and the code is translated to machine code in real time. And then in order to work, your profiler needs to get some input from this just-in-time compiler. And the question is, can the just-in-time compiler provide this input to the profiler? Some of them can. Ideally by default. Sometimes you need to recompile them with different flags. Sometimes you need to patch them with something that a shady person on the internet wrote. And other compilers do not support this at all. So it depends. You need to study for your specific programming language and the compiler. And finally, we get interpreted implementations like CPython for Python. That's a reference Python implementation, Bash for shell scripting. And those will always need tooling that's specific to the particular interpreter. Because if you run something like perf on a program implemented in such a language, what you will get is a performance profile of the interpreter. You will see, oh, the Python interpreter spends a lot of time executing functions. That's helpful. Not. So yeah. As I mentioned, I need to scope this presentation so that it fits in 2 hours. So I will focus on perf record, another tool from the perf suite, which is specialized to programs that use an ahead-of-time compilation model. Perf record works in 2 different steps. First, you run a first tool that's called perf record, which wraps a command, a shell command that you would otherwise type. And you can give it one argument, which tells about the sampling frequency. So what's all of this? The way perf record works is that it tries to find in which areas of your code a certain hardware event is occurring most often. The default event that perf studies is the passage of CPU clock cycles. If you study in which program you spend most of your CPU clock cycles, in human language, this means you are studying in which area your program spends its time. Actually, life is a bit more complicated than that because hardware does not support checking every 100 times per second. What it actually supports is, the operating system kernel tells hardware, hey, wake me when this 1,000 million CPU clock cycles are executed. And then perf will need to do some kind of calibration to adjust this so that you get the desired frequency. Now you have this data. And what you will be able to do next is some statistical processing to find in which area of your code you spend the most of your time, you're doing more level 1 cache misses, etc. That's a bit too fast. Yeah, that's because I wrote it the wrong way. One problem with this basic mode of operation is that very often perf will tell you, well, I have good news for you. You're spending a lot of time in some utility library, malloc, dynamic cast, random number generation, BLAS. And in a way, that's some information already, but if your code contains millions of different points where some memory is allocated, knowing that you spend time in malloc is not that helpful. You can get around this by using another feature of perf, which is stack trace sampling. So before, what perf used to do is to check at which point of the code you were. No, it doesn't stop there. Like a debugger, it will go and say, okay, I'm in this function, but who called this function? So it goes to the caller. And then who called the caller of this function? It goes up. And at some point, ideally, you know that from the main function, I call this function, which call this function, which call this function, and now I'm here. And there are several ways to measure this stack trace information, and unfortunately, all of them are bad in some way. The least bad option is to use debug information, like debuggers do, because since debuggers use it, it's the most well-supported way. And because perf needs to do the work of checking stack traces like 100 times per second, 1,000 times per second, it cannot afford to do the full stack trace reconstruction. So what it does instead is it copies the top of the stack of your program, and later, as a delayed analysis, it will try to analyze the top of the stack of the program and figure out the full stack trace. Hopefully, you will have recorded enough data to get the full stack trace. But if you are allocating lots of objects on the stack, this may not happen. Worse, this is also quite expensive in terms of bandwidth you're sending to your data file per second when you are recording a profile at high frequency with large stack samples. It's very easy when using perf to be bottlenecked by your storage device. And that's where some cool tricks come in. I mentioned earlier the sampling frequency. If your program is long running, this parameter does not need to be high. You can sample the program even only 10 times per second. If you have a minute of execution, that's more than enough. To avoid being bottlenecked by your storage device, if you have tuned your sampling frequency and stack sample size in such a way that the data file is not too big, you can put it in RAM using tricks like dev.shm on Linux. And this means that you have a lot more bandwidth at your disposal and you're less likely to be bottlenecked by the speed at which you can write profiling data on disk. Once you have the data, you can display it using another tool from the perf suite called perf report. What perf report does is it does a histogram of which functions the event of interest happened most often. So in the default mode, it just histograms how much time was I in malloc, how much time was I in BLAS, etc. But you can configure the grouping. You can say, maybe I'm not interested in functions. I want to have a coarser view, like I want to see, in a multi-process program, which process was using the most CPU time, or which of the libraries I'm calling I was spending the most of time in. You can get to the granularity of source, line of source code, But you need to be careful with this because the mapping between assembly instruction, which is what perf sees, and lines of code in your program is not obvious due to optimization, and you may get some tricky things in there. If you have stack traces now, you get a more hierarchical histogram, where you have a top-level histogram of which top-level program function you spend most time in. Ideally, this would be 100% of time in main. That's what you would expect in C, at least in a single-threaded C program. And then for each of these functions, you check, okay, then for each inner function that I called, which percentage of time did I spend on it, and recursively. Again, to get stack traces, we need some data, typically debug information, and this means that it's at the time you run perf reports that you need to have full debug information for your program and any library that it spends a significant amount of time calling. The good part of perf report is that as a textual user interface, it's very easy to run on your SSH server. The bad part of perf report is that as a textual user interface trying to display very complex statistical data, it's not the easiest to use. In particular, as soon as your program has multiple threads, I recommend using a different tool. And that tool may surprise you. It's Firefox Profiler. So what does Firefox have to do with this, you may ask? Well, you know, web developers have performance problems too. One of them is called JavaScript. Because of that, they have developed over time very fancy profiling tools that let them study, you know, when a particular web page is rendering, executing code, what happens across the entire system stack. And on Linux, to profile this whole system stack, they use perf, which means that this tool, which is initially intended for performance analysis of web applications, can perfectly ingest also data that was acquired on local applications. It will just, you know, display it a bit weirdly. You cannot just hand over your perf data file to Firefox because, you know, remember, it's just copies of the stack of your program. Firefox has no idea how your program stack is laid out, what is the debug information, how is the program stack structured. So we need to use a tool called perfscript, which can generate this high-level, human-readable information with some parameters. And then you send that into Firefox Profiler, and you get a cool visualization that we will see next. This is a great companion to perf report. For most purposes, when you're doing simple things, it's much easier to use than perf report because it's a real web user interface, not a text user interface pretending to be a graphical user interface. And it's very powerful when it comes to analyzing programs that have multiple threads, multiple processes, or behavior that changes a lot over time. One of the price to pay is it's less configurable. In perf, you can, as I mentioned, change the histogramming. You can say, I want a histogram by library, by process. This won't happen here. It only supports histogramming by program function. And there is one very cool feature, which is that once you have a profile visualization in Firefox Profiler, you can upload it on some unknown server somewhere on the internet, which is not great from a data governance security point of view, but is absolutely awesome when you need to share a performance program with someone who does not know to use perf and will never learn how to do so. Then you can just directly share the high-level information and they get the overview of how their program spends its time and they can work with it already. So that's really nice. When you look out on the internet, you will often see suggestions to use a different graphical user interface called Hotspot. I would not recommend it because every time I've used it, it has been so buggy that I could not do anything useful with it. I spent more time working around bugs than doing performance profiling. So, demo time after the water break. For this demo, because it's about narrowing down where code spends its time, we are going to look at a more advanced program, one that has a few thousand lines of code. extremely complex. That program is called T-Physics, sorry. And it's a love letter to the way programs are typically written in the particle physics community, particularly when it comes to performance. So it features lots of object-oriented programming, lots of dynamic memory allocation, all the good things you know are amazing for program performance. And that's a problem for us. Because now, you know, we have this relatively large program, and we don't want to try optimizing each line and see what helps. We really want to know, okay, which functions are the most critical to performance, where should we spend our time, especially as this code is much higher quality than the actual particle physics code you will end up in if you are doing particle physics. So what do we do then? Well, we use the tool we've just learned, perf record and perf record. Let's start with a simple run. Runs for about 10 seconds. Just, you know, we have config time to acquire lots of data in case we need to lower the frequency of sampling or something like that. At the end, it dumps some data to a file called perf.data. You can see that for simple profiles, this data is relatively small. We have 37,000 of program instruction samples in 10 seconds, which means we are sampling at 4,000 hertz, I think, about 3.7, 3,700 hertz. Okay. So lots of data. Normally, we should be able to do something with it. Just to show, you can actually look at the data without analyzing it with perfscript. And what you will see is that in the beginning, perf tries to take one sample every 144 clock cycle. After a while, it starts to get an idea of what's your clock frequency. Then it tunes up your clock, the interval between two samples to get to the expected sampling rate. And then it starts running your program and you get some functions, you know, every n sample. Okay. If we put that in a histogram form, we start seeing some stuff. So there is something about linear algebra operation. That's not entirely unexpected. I mean, this is a many-body problem with a very bad physics simulation of electrons, protons, and neutrons interacting with each other. So you would expect the math for that to figure some linear algebra. But there's more than this. The second function where we spend 12% of our CPU time is something that has dynecast in the name, which means that we are doing a suspicious lot of dynamic casting in a C++ set. We know if you've been doing C++ that this can be a bit expensive, so maybe we want to do it less often. Then we see free, at least part of the implementation of the free from the memory allocator from standard library. See, again, 10% of time in there. And it's worse than this because actually in a C++ program, you have some time spent in the C++ allocator, which then calls into the C allocator, which itself has some inner utility function. So spread across several of these entries, you see that we spend a huge lot of time doing memory allocations. Finally, we get some physics. Yeah, we are spending like 6% of our time in there doing some nuclear physics. Then more malloc, more dynamic cast, something about linear algebra, doing steps of the simulation, that sounds good. Interaction with charged particles, why not? Exponential, that might be a bit expensive. Comparing strings. What's going on here? Well, actually, this is comparing bytes of data. But you get the idea. We are doing stuff which is not stuff that physics application should be doing. At least not spending a huge amount of time on if it were written in a more performance optimal way. And this becomes more obvious if we change the way Perf report reports data by using a coarser granularity of programs and shared libraries that the program uses. And here what you will see is that we spend 42% of our time in code that we wrote, 30% of our time in the C++ standard library, which, as we know, we mostly spend doing dynamic cast and malloc, new and delete to be precise. Then 22 times in the libc, which, as we know now, are spent in malloc and free. Then a bit of math, whoa, yeah, and a tiny bit of time in the Linux kernel. Okay. So we spend about half of our time doing physics and half of our time doing stuff we shouldn't do. That's some performance optimization potential there. But yeah, as I mentioned, this is still not very actionable information, right? I know I'm doing dynamic cast. If I look in the code, I'm doing it in several different places. I'm doing memory allocation in several different places. So why am I calling these functions? And that's what we are trying to figure out next. For that, we are going to use hierarchical profiling mode. Unfortunately, because AMD performance counters are not as nice as Intel's, I'm going to need a slightly more complex version of the command I put in the slides, which is a big AMD-specific hack, but trust me, it works. And at the end, after 10 seconds again, we will get some results. Notice, by the way, that before we had a file that was 1 megabyte. Now it's 500 megabytes. As I mentioned, call graphs are expensive. Only use them when you need them. That's why they're not enabled by default. Then we load our data file, which we have saved on a RAM disk, as you may remember, in order not to be bottlenecked by our storage device. And here we see something that I'm not terribly happy about, which is that our stack trace reconstruction efficiency is very bad. Here, Perf only managed to trace 37% of program stacks back to start, which is the beginning of the program, if you are libc, or main, which is the beginning of the program if you are a C++ developer. So yeah, the stack trace seems to have a few problems in there, and that's unfortunately I have not had the time to analyze this, but I think that's a problem with the debug information that my distribution packages. So I will need to get higher quality one, or do horrible hacks like run a different Linux distribution in a container. That works. But in any case, we need to be careful with this data, because only 37% of our stack traces get reconstructed. And it may be that the reconstruction process always fails in the same places, which will bias our profile. So when you see this sort of data, be careful with it. To be more quantitative, what you can say for sure is that these children time spent in this function and the function that it calls are underestimated. The actual percent of time we spend calling a particular function will not be smaller than what Perf shows, but it will likely be higher, and we don't know by which amount. When you have to deal with this sort of low quality data, which happens more often than I would like using profilers, then it's helpful to use a different kind of display, which is called an inverted call graph. So this works like this when using Perf. You use different options. You will see, by the way, a list of all the commands that I'm calling in the text file that's attached to this course, which is the commands I'm running over time. And now what we get is something that looks like what we had before. So we see where in our program we spend most of our time, but with a little bonus, which is this little plus sign in the left-hand column. If you highlight anything and you type plus on your keyboard, what you will now see is the colors of a particular function as estimated by Perf. You can quickly check that the sum matches what's written above, which tells you that here's the stack trace reconstruction went well. And you can drill down, like, okay, this stuff do didn't was called by itself. Well, that's weird. I don't remember what that means. In any case, you see that it was called by __ dynamic cast, but here the stack trace fails. We don't actually know who the caller of this was. So this is where we need to start being careful. If we look at C3, we see that it was called by several functions, which such as int3, that sort of stuff. And if you could go up enough, which unfortunately here we can't, you would see who called this. Here we get stuff that's more interesting. Like we see that dynamic cast involves memory allocation. So some of our memory allocations come from dynamic casting. Not very high quality data, unfortunately, but there is some stuff in there, and as you will see, we can do some things with it. However, again, when you have low quality like that, perf report is not the right tool. We need something more powerful. So here, we are going to go for Firefox Profiler. And to do that, as I mentioned earlier, we are going to need to export the data into a format that Firefox Profiler can understand. So we do the export. Take your web browser, go to profiler.firefox.com, load the profile, which is here, and we get this view, which I will zoom in as much as I can before it gets unreadable. So there's a lot of information in there. At the top, you see a timeline. And by looking on the right of this timeline, you get the first piece of information, which is how much time your program took to execute. So again, 9–10 seconds. Below this timeline, you see a list of all processes and threads that were active at the time where perf took some data. By default, Firefox Profiler only shows those that had a significant amount of CPU activity. But if we need to see everything, we can. We just enable it, and then we see that indeed there is something called perf, which did a tiny bit of CPU work at some point, negligible with respect to the main application. We can ignore it. Something called swapper, which is basically what the kernel does when it has nothing to do. Something called softcirq, which is a kernel handling hardware stuff, like when hardware tells you, hey, kernel, I need to do something. That's the kernel thread that gets awoken. Another stuff that's about, I believe, network cards, I'm not sure. But yeah, all those are indeed tiny, so Firefox Profiler was right to hide them by default. Each of these lanes is interactive. You can put your mouse anywhere, and you can see the sample, stack sample taken by perf, which is closest to where you are pointing. This can be a quick way to skim to your data and see if the application seems to have some execution phases. Another thing you can do is you can select the time range. And this will only show you the samples that are associated with this time range. That's very helpful when you have programs that alternate between doing different things, because then you can easily study these things separately. You can zoom in to what you selected to get a better overview. And if you do it enough, and by enough I mean quite a lot, you will start seeing your individual stack samples. This is helpful when you're looking at a particular kind of performance problem which exists in multi-threaded application, which is threads that are waiting for each other. If a thread is waiting, it's not using the CPU anymore, so you will get no samples for some duration of time. So if you see gaps in the blue dots on this timeline, it means that your thread is blocking on something. That's interesting. We can do something with that.
What is exactly the blue dot?
There is one blue dot per sample of the stack that perf took. Here, unfortunately, as I mentioned, on this particular machine, the stack traces are low quality, so it's not always very nice. But here you get a good example. So you have start, which called libc start, so that's libc internals. Eventually, it calls the main function of the program, which called tphysics step, which called the particle interact with, which called the interaction function for nucleons, which called some vector operation, and then which called some std function, and that's where we spend our time. So we get little snapshots of what our program was doing at one specific time. And by checking if the time distribution is even as it should, we can check if sometimes our thread is stopping, however crudely. There is a breadcrumb at the top. Anytime you do some operation in Firefox Profiler, you can go back by using this breadcrumb. This allows you to go back to some point, but not all the way. Like, oh, I just zoomed in too much. I can go to the previous step without, needing to have a Control Z, which only works for the very last action you took. So that's nice user interface design. Below this overview, we get a view which is similar to what perf reports displays by default. As I mentioned, unfortunately, on this laptop, I have low quality data, so I do not trust this. Yeah, that's time selection is independent for zoom. That's something you need to be careful about. I do not trust this data, so I need to use an inverted call graph instead, and then it mostly works as in a perf report. One cool thing is when you select a function, there is some highlighting which allows you to say which samples were associated with this function. Again, this is very helpful when you want to see if your program has execution phases. Like, are there some points in the program where you spend more time calling specific functions than others? Another thing you can do with any kind of function name in Firefox Profiler is right-click on it. And this provides a couple of interesting options. One which I would like to mention is collapse. What this does is, if you have a function A, which was called by a function B, when you call collapse, it will add the time spent in function A to the time spent in function B. That's very helpful when you have stuff like memory allocation or dynamic cast where you have several utility functions calling each other. By using this operation enough time, you can get an idea of how many time do I spend doing dynamic cast overall, even without good stack trace data. Another cool thing you can do is a flame graph. So what is this? This is a visual representation of the stack traces as a hierarchical histogram. So the horizontal axis is which percentage of time was spent in a particular function. And as you go from the top of these flames and go down, you see I was in this function, which was called by this function, which was called by this function, which was called by this function. And at the bottom, you should see start if your program was acquired perfectly, if your profile is perfectly correct, which in this case, unfortunately, it isn't. You can zoom in using the focus on function mode. This is a bit more powerful than what it looks like. When you use this functionality, you do not only see the function you have, the one occurrence you have selected in the flame graph, you see all occurrences everywhere in the flame graph. Which means that if you have some stack reconstruction problem, where some functions were not fully reconstructed up to their color, you can recover some correct information for these particular functions. Let us zoom in on our correct functions for now. And we see that start, code, and yeah, we get to the main simulation, we get interact with, and almost all stack traces that perf acquired did this. So this is not very interesting information. We see that we are bottlenecked by particle interactions, particle-particle interactions. So let's make our visualization easier by zooming on that. Then we see that among particle operations, we have interaction between charged particles, interactions between nucleons, linear algebra operations, destroying linear algebra vectors, that gives you a hint about some of the memory allocation we've seen earlier. And proton-proton interaction obviously are more expensive than charge-particle interaction and nuclear interaction. And the reason why I say obviously is that if you've done physics, a proton is both a charged particle and a nucleon. So what this function does is actually called interaction between charged particles and interaction between nucleons. We can look at overall time spent in processing nucleon-nucleon interaction. Again, we see vector operations, which end up calling something that allocates STD vector. Hint. We see dynamic cast. We see some exponentials in there. Lots of dynamic cast. So, that's some data we can start working with. We see, okay, we're in this function. Clearly, we are doing too much dynamic casting. We need to do something about that. We have a very bad linear algebra implementation that does lots of linear memory allocation, and we need to fix that. And once we've done all that, maybe we can start thinking about whether our exponentials are expensive, but right now they are not that big of a concern. All right. That's all I wanted to show for this particular program in Firefox Profiler. Hopefully, even if I didn't manage to have top-weighted data, this shows you already how it can be useful on a real-world program to understand how, where you spend your CPU time. And again, this is just one operating mode of path record. You can also study where you go outside of your cache, L1 cache, for example. It's just a matter of switching to a different hardware event. So that's power. I have 15 minutes left, so I will go quickly over what I have left and skip a bit. So when you do hierarchical profiles, you have two profiler parameters that will increase overhead. One is how frequently you are taking samples, and one is how big your samples are. The former gives you more time resolution. The later gives you more stack trace resolution. You get deeper stack trace. Here I have an example of a data acquisition program where I needed to use both to get a full overview. If I put a lot of time resolution with tiny stack traces, then I can see that I have threads blocking on each other. And if I put big stack samples, then I can get a better view of the overall control flow of my program. I get deeper stack traces that give a better picture of what the program is doing. What I would like to show now, because you will not get another chance to see this data easily, is some data from a Python program, which was acquired using a different profiler called PySpy, which I highly recommend using. This data was acquired by a colleague using advice from my side. And as you can see, PySpy produces flame graphs, just like Firefox Profiler. It's just that, yeah, they look less good by default. Unfortunately, there is a nice alternate visualization available. Unfortunately, the colleague did not keep the right data file for me to show it to you. The flame graph is showed reverse in PySpy. So on top, you get all the program, then you get each thread or process, then you get main function, calls of main function, and so on. You can, but the interface won't let it show you because the command line is too big. Search for functions that have a specific string in their name, which lets you see when you have recurring patterns in your flame graph. So that's a way to get the same sort of stuff that we had with focus on function in Firefox Profiler. And we can double click on something to take a deeper look at it. I look here, for example, and I zoom in a bit. What you can see is that we spend a lot of time calling something called torch : autograd. So, the first time I saw this name, I say, okay, that sounds like a town in Russia that manufactures cars, but that's probably not it. And indeed, that was not it. It was an automatic differentiation engine. And what transpired is that actually our machine learning framework need to do automatic differentiation for various things. And they make it so easy to use that it's very easy to do it when you don't need to. And then you spend a lot of time in automatic differentiation where you probably should spend that time doing other things. And by fixing that, he gained a very nice speed up. Again, this is the sort of thing you can only find using profilers. You would not find it by chance. To conclude, I have not said so far what needs to happen once you have found some hot functions. The general strategy here is to take the part of your code that's performance critical and extract it into a smaller program that's easier to run, takes less time to run, so on, so that you can throw many tools at it and study it in more depth. Example of tools include manual assembly inspection using tools like Cutter or godball.org. Static analysis using tools like compiler, optimization reports, Macao. Dynamic analysis using tools like another perf functionality, which I do not have the time to show you, which shows you how you spend time in your assembly instructions. So what are your hot loops, that sort of stuff. Intel PT, which is an absurdly powerful hardware feature that allows you to record a detailed trace of every single instruction that was executed by your program and at which time this instruction was executed. And if all else fails, you can always, add some print statements or whatever to your program to record additional data. Once you found why you're reaching the hardware limits that you have identified previously, then you can start thinking about how you can optimize it. And because you've been careful and have kept this small fragment around, it's a very good idea to often, as you try to optimize, go back, run again, and see if you've improved something, degraded something, have a tight feedback loop. I try something, I run the benchmark again. Has it changed? No. I try something. Has it changed? Yes. For the better, hopefully. You see the idea. To conclude, profiling is about understanding. You start with a program that's not as fast as you would like, or maybe you're just wondering if it could be faster. And you want to understand what's going on. You start a general purpose tool, which will give you high-level information like which hardware is limiting your execution time. And then once you've identified the right hardware, you drill down with more and more specific tools that will provide more detailed information that you can then use in your optimization process. I advise to go very slowly at the start of the process and be very sure of what you are thinking is true, because getting the early stage wrong, as I mentioned, will cost you. You will end up optimizing CPU and a program that doesn't need to have efficient CPU execution. Most performance analysis tools are specific to either your programming language, your operating system, your hardware, and sometimes a combination of this, which means that we have many tools. Too many for you to all start learning at once. It's a good idea to, start asking questions, go to your performance experts. What tool could I use to answer this particular question? Oh yeah, you can use that. Then you learn this one as you need. Later, you ask yourself a different question, you learn the appropriate tool for this question, and so on. If you want to dig deeper in this topic, two big authors that I highly recommend you to look into are Brendan Gregg and Denis Barbalov. Brendan Gregg is a Linux performance analysis expert. He's previously worked at Netflix, making the Netflix infrastructure not die when thousands of people are accessing videos at once. So he's kind of system administrator, but with an ability to think about performance as a whole of the whole system, not just one particular application. That's something very precious, again, as I mentioned, in the early analysis stages, even if you are a developer. His website is messy, but if you take the time to dig into it, it's full of very useful information. If you're looking for something more structured, he has authored two books, one which is general purpose, one which goes into more advanced tooling based on the BPF system on Linux, which allows you basically to inject arbitrary code anywhere in your kernel or user space program in order to extract information from it. Denis Barbalov is more someone who has experience with CPU-related concerns of performance optimization, particularly on Intel CPUs. His blog is low volume and full of very nice articles, so I strongly advise you to subscribe to it if you're interested in this topic. He has also written a book, and because it's much smaller than the books from Ben and Greg, I have taken this one with me. So if any one of you want to borrow it to see what it's like and decide if you want to buy it or not, go ask me later. That's not all in terms of tooling. As I mentioned, languages have specific tools. Each hardware manufacturer has their own tooling, which is a huge pain, because now if you are trying to port your application across many hardware, you need to learn that many different tools, which is a pain. Thankfully, as I mentioned in my architecture course, often optimizing things for one hardware helps for other hardware as well. And in the specific case of HPC, there are a few profilers that are specialized to the HPC use case. They can handle things like MPI, which other tools cannot. Unfortunately, as it turns out, HPC engineers are not experts in software packaging, so good luck if you want to install them on your system. It's better to be on an HPC center where someone has already installed them for you. That's it from my side. I will now proceed to take questions from the room and from Discord.
Is there any chance that we could get the perf file from the simulation you ran just to run the Firefox profiler locally, or no?
You can, but given how low quality the data from this particular laptop is, I would like to generate some higher quality data before handing it over.
Fair.
Otherwise, you know, if you have a perf working on your machine, you can profile it yourself. It's a very simple C++ program. You just run make, and if you have a C++ compiler, it works basically. So you can also give it a try to profile it locally. This is a good occasion to get perf working on your machine. If you run into any problem, ask me, I can help. What? Yeah. So the book of Denis Barvalov that I mentioned earlier looks like this. You will find it on his website along with his blog. It's a good one. And I am not paid to do this advertising. It's just really good. Yeah.
So first to thank you for the presentation. What actually advice would you give to the developers of this program that we looked into?
So given what I have observed, my first advice would be to basically what I have right now is a heterogeneous list of particles of different kind, and which are each modeled as different objects that have a common base class. And they need to do some dynamic casting to handle particle-particle interaction.
Yeah, dynamic casting is always a bad idea.
A better way to do this would be to have 3 particle lists, one for electrons, one for protons, one for neutrons. We have only 3 particle types, so that's tractable. And once we have that, we don't need dynamic casting anymore. We can just say, okay, I want to do electromagnetic interaction. Electrons interact with electrons, with protons. I do the interaction. For small pools of classes, that's a lot more efficient than object-oriented programming. And in particular, it will get rid of the dynamic casting bottleneck. Once that is taken care of, hopefully the program will be about 2 times as fast. Then we can start thinking about this linear algebra library. Maybe it should just be completely replaced with something written by slightly more competent people like Eigen. If not, we can think about how we can stop doing dynamic memory allocation in our linear algebra library. Here we are only manipulating 3-dimensional vectors, which means that instead of using std vector to store vector coordinates, we can use std array, and this will remove 1 memory allocation per vector we create, which is good. Alternatively, for better performance, again, we will want to have to flip the data layout around and have vector of x coordinates, vector of y coordinate, vector of z coordinate, because this will make things like cross products more efficient. You cannot do efficient vectorized cross product if you have a list of 3-dimensional vector one after the other. You want to have a coordinate-wise arrays.
But how did you find this out from the trace?
I would find it first by finding that I spend a lot of time on cross products. And then from this, I would start looking at literature about how other people are doing lots of cross products in their program and figure out, oh yeah, there is this vectorization thing I need to take care of, and people say it's better that way. For common problems, studying what other people have done is a very good idea.
You went down to the code at some point. to the code
Yeah.
at some point. Yeah.
And then there is a bit of experience as well. Like after a while, you start knowing that specific areas of the language are particularly dangerous.
And I didn't really understand, was this run only on one node or on many nodes? Because in the beginning in the perf tool, we were just observing one node, but when we went to the Firefox profiler, you could see communication like synchronization problems.
So the one I have shown, which has communication between threads, is from a different program. For this particular program, I ran everything in one node because that's easier to profile. So I do a local UDP communication instead of doing across two systems. That happened to work. And then I could study, the threads that send data, the threads that receive data, how they interact with each other in time. If you did something like MPI, a better way to do this would be to use one of those profilers I mentioned, which are a pain to install, but handle MPI seamlessly so that you can get a synchronized timeline across all your MPI processes.
So perf can only profile on one node?
By itself, yes. If you want to profile multiple nodes, you will need to do some post-processing of your data to combine the data from different nodes.
And in your job, you use Firefox profiler?
Yeah, it's a super
And
convenient
it's okay
visualization
to
of perf
upload
profiles.
all your traces on the web?
I share it when I consider this data not terribly sensitive and it's more convenient to just hand it over to colleagues so they don't need to run perf themselves.
But this is your only visualization tool that you use?
That's the main one I use when I care about things like threading, multiprocess, and synchronization. Or more generally, when my data starts to be too complicated for just perf reports. One important thing to note about Firefox Profiler is that by default, it runs locally on your machine. Uploading a profile to some random server on the internet is an action you explicitly take. You can do all the analysis on your computer with the data resident in RAM. It doesn't go to a server.
With the Firefox profile?
Yeah, that's the default.
That was my question. And also, to mention, last year I studied Paraver, which is like a very powerful profiling tool. I was surprised it's not in the list. This is why.
I would put it in my HPC profiler that I never managed to go to work on my machine's list. Again, if your HPC center has taken the time to install it and get it to work, great, use it.
Yes, and I've heard also Gromax is also very useful for some applications.
Is it possible to have statistical metrics for the perf profiler?
Sorry, I don't fully understand you.
Yeah, my question is it possible to have a statistical metrics for the perf profiler?
Something like perfstat?
Yeah.
You don't need it. You could get it from the raw output of perf scripts, but it's not the best way to get it because what perfstat does actually is, you have this counter that counts events in hardware, and you just check the initial counter value at the beginning, check the final value and subtract, and you get how many of these events you had. So it's a very efficient process, whereas in your profiling, you're constantly interrupting your program, which you need to carefully tune the sampling frequency to get good overhead. Then, because you're not checking your program all the time, you need to be a bit careful when you're estimating the total number of events, because that's a statistical estimate. It's less precise than when you do it with just a subtraction. So for all these reasons, if what you want is statistics, I would advise rerunning your application with perfstat. Again, if you have something performance critical, make it fast to run so that you can easily test it with many different tools.
For MPI calls, for example, what would you use to examine?
I would
MPI
look
calls?
into the HPC ones and take the time to get them to work.
Please repeat.
I would look into the HPC profilers that are specialized for this and take the time to make it work. It's really the one thing they do really well, much better than anything else I currently use. I can afford not to use these tools because I rarely deal with MPI application and mainly focused on node local performance in my studies.
Thank you.
Maybe if there's no other question in the room, I will look into the chat. So, what does the chat say? Nothing here. Why perf mainly? There is an entire slide about this at the end. Yeah. Basically, if you compare perf to any other CPU profiler I know, it's the most flexible tool I know of. One unfortunate consequence of this is not the easiest, but I think learning it is worth it because you can do so many things. To give the full picture, with perf, you can do multithreading. Surprisingly, that's something that many profilers struggle with, still to these days. If you have ever used gprof, it produces garbage on multithreaded program. gperf tools, it can handle them, but the result is very hard to read. Valgrind, its vision of multithreading is let's alternate between executing each thread in a sequence, which is too slow for any realistic application, especially because Valgrind is also typically a slowdown of a factor of 30. Microarchitecture are things that these two tools do not do that well. Basically, as you can see, the main competitor of perf in how flexible it is Intel vTune. And here, the main benefits of perf is it can give you greater insight into the inner working of the C standard library, mutexes, malloc, stuff like that, using something that I don't get into called user space defined tracing, or just code injection inside of libraries to get information out. It can instrument your code, as I mentioned, which is very convenient when you have some data that's hard to get otherwise. You can get it from code that you do not need to recompile, which is very useful with proprietary code like NVIDIA library, sort of stuff. It can trace the activity of your operating system. You can see system calls, answer questions like, how often am I calling the right system call to write to a file with which size of data? It works, but that's similar. And yeah, most importantly, even if you will not always get the same matrix, it works on any hardware, whereas Intel vTune, as you guess, mainly works on Intel hardware. It kind of those basic stuff on AMD, but you quickly run into stuff. Okay? That's why perf.
Perf is language agnostic?
It works for all ahead of time compiled languages because it's based on analysis of the ELF file format. Executable and linkable format, which is a format used by all binaries and libraries on Linux. You may manage to get it to work with JIT compiled languages, but it may or may not work. That's implementation dependent. That's something else. That's something else. That's something else. That's something else. So no other question on Discord. Room, this is your last chance. Do you have any other question? If not, I propose we wrap it up for today.
Okay, so thanks for joining us today. So we'll stop here. We'll start tomorrow morning at 9 o'clock as usual for some stuff with cycle. And then we'll have morning full with cycle and then an afternoon full with Fortran on CPU. So hope you will also learn a lot of interesting stuff. And see you tomorrow and bye.